All righty. Tell me things about equilibria. Yep. The rate of the forward is equal to the rate of the reverse. Okay, what else? Yes? Has to be a closed system. What else do we know about equilibria? Yes? You need to have both products and reactants present. What else we got? Yes? You need to have a constant temperature, yeah. What else? Yep. Sorry?
Reaction itself must be reversible.
Reaction must be reversible, yes. Excellent. Anything else? That's 1, 2, 3, 4, 5. And I think I gave you 5 on that little list there. All right. So what is the definition of a dynamic equilibrium? Have a little chat with your neighbor about that one.
Definition. Dynamic equilibrium is like the cartoon. And you're trying to balance out.
There were 3 things from that video. What were they? I don't know. It says 1, 2, 3. Question 2. 1, 2, 3.
No observable change.
No observable changes. You know what? I don't even know. I don't even know what it's supposed to be. Let's forget that question just for now. We'll come back to it later when I remember. Because, okay, there's different ways of looking at equilibrium. You can say there's things that must be true in order for an equilibrium to be present, right? And then you can say, what is the definition of an equilibrium? And that means something slightly different. So I don't want to get the two mixed up for you. So we're just going to stick with this and then we'll carry on and get there eventually, okay? So coming to equilibrium, this is looking at rates. This is on page 5. So most chemical reactions look something like this, where we got a one-way arrow, carbon plus oxygen gives carbon dioxide, let's say. Carbon dioxide, once formed, it will not break back down, so we have a one-way arrow. Most reactions, though, sorry, not most reactions, in other reactions, we have a two-way arrow, which we show as a double harpoon. And if you're not sure what a harpoon is, it's one of those things that the whalers used to stick into whales to go and get them. Okay, so 2 harpoons. The top arrow represents the forward reaction, and the bottom arrow represents the reverse reaction. So it tells us that NH4Cl can break down, NH3 and HCl can get back together. So there's our forward reaction, there is our backward or reverse reaction. Because both of these reactions are taking place, we call this a reversible reaction. And it is important to note that forward and reverse reactions can take place at different rates. Okay? No problem, they can be at different rates. It's just not at equilibrium if the rates are different. EQ with little m, what does that stand for? Equilibrium. Yeah.
In order for the forward and reverse flow to be separate, if it's the forward and the reverse flow have the same magnitude.
No, that would be impossible. Or close to impossible, because that would mean the potential energy of the reactants and the potential energy of the products were the same.
But how does the same possible?
Because it is, you reach a point where the entropy and the enthalpy are minimized and maximized as best they can, and it reaches a state where it's like in balance. Yeah? It's where delta G is equal to 0. Okay? Don't worry about it. We'll get to delta G more later. Okay? For now, just believe me, forward and reverse rate are equal at equilibrium, and no, they do not need the same activation energy. Let's say we place some NH4Cl in a closed container. At the beginning, so here's the beginning, we have loads of this, tons. How much of the product do we have at the beginning? We have none, okay? None. So our forward rate is fast. That's supposed to be an exclamation point there. Okay, what about that reverse rate? The reverse rate is how much? If we have no products, what is the reverse rate? It is 0. You can say it out loud, it's okay. You know what you're talking about. Okay, so the reverse rate is 0 because if you don't have any products, you cannot form reactants. Also, at the beginning of the reaction, since there is no, okay, that just says what I just said. Okay, so at the beginning, we have no reverse rate reaction yet. Okay. If we graph the rates of the forward and reverse reactions, so on our x-axis, we have the progress of the reaction, so the reaction is proceeding. And on our y-axis, we are graphing the rate. And the forward rate is going to do what forward rates usually do. Does the rate usually start out fast or does it start out slow? It usually starts out fast. And then what happens to it as the reaction proceeds? It slows down. Okay? So in the beginning, we have an initial rate, which is fast. So this is our forward rate. And then we have our initial reverse rate, which is nothing because there are no products. All right, there's our little diagram there. Use the reaction above to help choose the correct responses. As an upshot of this, at the beginning, are we using up NH4 faster or slower than we are producing it? Are we using up NH4 faster or slower than we are producing it? We are making it faster. We're using it up faster than we are producing it. So what will happen to the concentration of NH4Cl as time goes on? It will decrease. And if the concentration decreases, what happens to the number of collisions between NH4 particles, NH4Cl? There will be fewer collisions, which means the forward rate will decrease, which is what you guys said would happen. You said it starts fast and then it gets slow. Okay. Our reverse rate. Are we producing NH3 and HCl faster or slower than we are using it up? Or are we, what does the question say? It says we are producing, yeah. Are we producing them faster or slower? These guys. We are producing them faster than we are using them up. So we are producing our products faster than we are using up. Therefore, concentration of NH3 and HCl will do what? They will increase. So there will be how many collisions? More, which means the reverse rate is going to increase. All right. So here's what our little equilibria arrows could look like. This is still fast. Forward reaction is still fast. The reverse reaction, you'll notice there's no longer an X through it. It does occur. But is it as fast as the forward reaction yet? No, not yet. Okay. So, forward rate gets slower as the reactants decrease, and the reverse rate speeds up as concentration of products decrease. What do you think the rest of that graph is going to look like? Where will they end up? Right in the middle, okay? So they're going to end up right in the middle, which means they're going to be lying right on top of each other. And if they're on top of each other, that means the two rates are equal. And once the rates are equal, we are at equilibrium. Okay, so we've got that, we've got that. I don't know that we need to go through this. This is still the same thing. We've got a fast-ish reaction forward. We've got a slow-ish reaction backwards. So we are still using up NH4Cl faster than we are producing it. Therefore, NH4 will decrease, which means there will be fewer collisions, which means the forward rate will decrease. NH3 and HCl are still being produced faster than they are using them up. So as time goes on, their concentrations will decrease. So there will be fewer. Hang on. Did I do something wrong? Yeah, their concentrations are going to increase because we're producing them faster. Silly me. I don't know why I said that. Because my mouth was going ahead of my brain. So there will be more collisions, which means reverse rate will increase. And again, we can see that on the graph. And oh, look, just as you predicted, they are going to get closer and closer and closer and closer. So we're going to draw smooth lines connecting the two curves. We're going to label the forward and reverse rate curves and predict what will happen as the two carry on. Okay, so we've got our forward rate. And we have our reverse rate. At what point did we reach equilibrium? When the lines intersect right here, this is where equilibrium is reached. Oh, and we should label our reverse reaction. And I want, what is this one? This is 2.1b. Okay. I forgot to put the links in my notebook, so I got to grab them from here. I know they look like they're there, but you can't do anything with them. It's kind of useless. There we go. So let's grab it here. There we go.
In today's video, we're going to look at reversible reactions.
Okay, here we go.
And see what we mean by the terms equilibrium and the position of equilibrium. Now, most chemical reactions look something like this, with the arrow in the middle pointing to the right, to indicate that the reactants can turn into the products. This means that it's a one-way reaction.
Do you know what?
Once
I
the
think
carbon
this is just
dioxide is
repeating what I
formed,
just said.
it
So
won't break back.
you can watch this as a review if you would like to. Okay? Let's not watch it right now. Watch as a review if you like. And now we move on to 2.1c. The position of the equilibrium. When last we left our equilibrium system, the rate of the forward rate had become equal to the rate of the reverse reaction, which meant that we had reached equilibrium. Both reactions are still happening, but they cancel each other out. How do they cancel each other out? Reactants are being used up as fast as they are being produced. So we're using them up. Forward rate is using them up just as fast as the reverse rate is producing them. What does that mean for the concentration of the reactants? Chat with your neighbor about that.
No, I did.
What is happening to the concentration of reactants when we are at equilibrium? Is he okay? Anyone? Do you remember your, oh, you want to say something, sorry? Yeah, the concentration of the reactants are constant. Remember that hole that's being dug? We are digging up that hole as fast as the other person is filling it in. Okay, therefore the concentration of the reactants stay constant at equilibrium. Same for products. Oh, and look, it says it right here. The concentration of reactants and products won't change anymore. They are constant. But that does not mean that they are the same, i.e., the concentration of reactants does not equal the concentration of products. So reactants stay constant, products stay constant, but they are not the same as each other. Does that make sense? Yeah.
So means the reactants are exactly.
No, constant means they are unchanging. So if the reactants are at 1 molar, they stay at 1 molar. The products could be at 2 molar and they stay at 2 molar.
Isn't every equilibrium has like more
Yes. The concentrations are all constant, but they are not the same as each other. This could be 1 molar and it would just stay as 1 molar. This could be 2 molar and it just stays as 2 molar. They might be different. It just depends on what the particular equilibrium is. That make more sense? Cool, cool. All right. So here we go. We've got some NH4, Cl, and we've got some NH3 and some HCl. And we are at an equilibrium. And I say an equilibrium because what can change an equilibrium? What conditions are necessary for an equilibrium? We need a closed system. We need a constant temperature. What if I were to change the temperature? Then I would no longer be at equilibrium and I would shift to a new equilibrium. Okay, so we are at an equilibrium. This is the equilibrium at a particular temperature. And in this particular case, we have a lot less reactants than products. Not very much. Lots. But under different conditions, which is probably a different temperature, you might have way more reactant. Okay, so lots of reactant and very little product. This is also an equilibrium. In either of these cases, are the concentration of reactants equal to the concentration of the products? No, they are different. Will they change as long as conditions are kept constant? No, those will just stay the same. Huh? Hold on. This is at a particular temperature, and then the next one is at a different temperature. Yeah? So just because the concentration of products and reactants remains constant does not mean they are equal. The relative concentrations depends on the conditions present. So how do we describe the position of an equilibrium? If we have more products, we say the position of the equilibrium lies to the right. Another way to say that is that the products are favored in this equilibrium. Does that make sense? The equilibrium lies to the right. We got more products than reactants. It favors the products. It lies more towards the product. If we have more reactant, then the position of the equilibrium lies to the left. In other words, the reactants are favored in this other equilibrium. Now, it's the same system. We still have NH4Cl. We have just different conditions. Okay? The position of the equilibrium changes when conditions change. So the position changes when conditions change. So in this particular reaction, not all reactions, just this one, okay? Not all reactions. For this particular reaction, if we add heat to the system, in other words, if we increase the temperature, it encourages or favors the forward reaction. So what does that mean? If it favors the forward reaction, what are we going to end up with more of? We're going to end up with more products. Okay? So when heat is added to the system, we say that that equilibrium shifts to a new equilibrium position with more product. So this is our old equilibrium position. And during that shift, the forward reaction is favored, which means, what does that mean in terms of the two rates? If the forward reaction is favored, if we're making product more, in terms of the rates of the forward and the reverse. Have a chat with your neighbor about that. What does this mean in terms of forward rate and reverse rate? What do you think? Are those rates different? Are they the same while it is shifting? If we are shifting, if we're making more product, which rate is faster, or are they equal? The forward one has to be faster because we are ending up with more product, which means this direction is going faster, so we're ending up with more of this, and we're using up less of it, so we end up with more product. Okay? It's the same sort of a situation where you just put all reactant into a bucket, right? And you have the forward rate being faster and the reverse rate being slow, and eventually they come together. What's happening right now is we've sped up the forward reaction more than we've sped up the reverse reaction. So the forward rate is faster than the reverse rate while we are shifting. So we got a whole bunch of new language here. This shifting just refers to the position of the equilibrium. We shift from a position where we had the reactants favored What does reactants favored mean? Concentration of reactant is bigger than concentration of product. That's what reactant favored means, okay? That's where we start. And we're at equilibrium. Then we heat it. And when we heat it, that reaction shifts to the right. In other words, we are making more product. Right? We started out with a small amount of product. We started out with a large amount of reactant, and we're finishing with a small amount of reactant and a large amount of product. So we shifted to the right. The position of the equilibrium now lies, this new equilibrium. So this over here is a new equilibrium. That position lies to the right. The products are favored in our new equilibrium. Yes? Pardon me? Oh, are the products technically reactants? Yes, but when we write a reaction, we need something to call the stuff on the left-hand side and something to call the stuff on the right-hand side. So we always call the stuff on the left-hand side the reactants, and the stuff on the left-hand side on the right-hand side, the products.
So if you put the NH3 plus HCl to the left side,
then your whole thing gets flipped. Then if you move, like if you were to write this reaction backwards, the NH3 and HCl would become the reactants, and the NH4Cl would become the products. It's okay. This is it. Just go with whatever's written. Whatever's on the left is the reactants. Whatever's on the right is the products. And it's okay because the products react to form reactants, which is, and reactants get produced. Okay, but you'll get used to it. Don't worry. We'll spend like the whole rest of the semester talking about reactions like this. You'll just be like, by the end, you'll forget that it was ever mind messing with your mind. Okay? Okay, so products are favored. What does it mean that products are favored? Tell your partner. What does it mean that products are favored? There are more products. Concentration of products is greater than the concentration of reactants. And if you've not yet invested in some highlighters or colored pens or something, I would highly advise it. It's helpful. I also have a ton of highlighters at the back there just for use during class, should you so desire, by the free paper. Okay, so we have an old equilibrium. We changed the conditions, we changed the temperature, and it shifted. During the shift, the two rates were not equal. When we got to our new equilibrium, now the rates again are equal. Now, I'm gonna get a little ahead of myself now, just because it really almost lends itself here. What does increasing temperature do to a rate? It increases it. So when we increase the temperature, what happens to the forward rate? It increases. When we increase the temperature, what happens to the reverse rate? It also increases. But we know that the forward rate and the reverse rate are not the same. The forward rate is greater than the reverse rate. Anyone want to tell me what that means? Yeah?
It's like temperature, like so the reaction, like both of the directions overall rate, which the rate is equal to.
I'm not sure what that means.
You know how the forward rate is
Yep.
the forward rate is supposed to be the same, right?
Yeah.
So maybe they can be both.
Yeah. So let's say we have our forward rate and our reverse rate. They're equal. Yes? Now, they both get bigger. But the forward rate got more bigger. And the reverse rate got bigger, but not by as much. Okay? We will talk more about this later. There's like a whole section on it. Okay? So if that just went over your head, that's okay. And then the two rates will come back together, and you'll end up with the two rates being equal, but both faster than they were before. Okay? But like I said, that's at getting ahead of the game. So if you didn't understand that, just let it go. Now, removing heat from the system, if we are cooling the system, in other words, if we are decreasing the temperature, if you had to predict logically, what do you think would happen to the position of the equilibrium? In our initial equilibrium, who is favored, products or reactants? Products are favored. What does that mean? Concentration of products is greater than concentration of reactants. Okay, so this is our initial equilibrium. Then we cool it. What happens to the position of the equilibrium after we've been cooled? It shifts to the left. Yep. L for left. Okay. And now who is favored? The reactants are favored. What does it mean that reactants are favored? Concentration of reactants is greater than our concentration of products. How would we describe this in terms of the position of the equilibrium? In the initial equilibrium, what would we say about the position of the equilibrium? The position of the equilibrium lies to the which direction? Lies to the right. Okay, like I said, we're just getting this vocabulary. We're getting used to using it. The products are favored. The position of the equilibrium lies to the right. This is just another way of saying products are favored. What would we say about our new equilibrium? What would we say about its position? It lies to the left. So as we've said, when a system shifts, it moves from one equilibrium to a different equilibrium position. Systems shift in response to a change in conditions. This change in conditions, we're going to give that a name as well. That is called a stress. Yeah, we stress the system and so it shifts. Cooling or heating, there are others as well that will also cause a shift. While the system is shifting, the concentration of the reactants and products change. And that's because the forward and reverse rates are not equal. Once the system is finished shifting, we will have reached a new equilibrium, and the concentration of products and reactants will remain constant. So when we are finished shifting, the concentrations will remain constant because a new equilibrium has been established and the forward rate is now equal to the reverse rate again. They're probably both faster than they were before or both slower than they were before. But they will once again be equal. Closed system, regardless of the position of an equilibrium or the conditions present. If you do not have a closed system, you cannot reach an equilibrium. A closed system is a sealed environment where you cannot have mass transfer, so there's no mass transfer in a closed system, but heat can come and go. Heat can come and go out of there. In an open system, you get both mass and heat. That does not always mean you need to put a stopper on it. You only need to put a stopper on it if there's gases. Yeah? If you've got something in aqueous, if you've got only aqueous reactants and products, are those aqueous things escaping the water? Or are they staying in the water? They're staying in the water. So a closed system can just be all aqueous things in water. Or, you know, if you've got a solid that you throw in there as well, that's fine also, okay? A closed system does not allow for any substance to escape, but it does allow for the transfer of heat, which can lead to a shifting in the position of the equilibrium. The last thing we need to cover is that reversible reactions are always, and hopefully this makes sense, exothermic in one direction. And if they're exothermic in one direction, what do they have to be in the other direction? They have to be endothermic in the other direction, right? Because if we look at our little graph, that one, the forward is endo, and the reverse is exo. There's no choice. If one goes up, the other has to go down, right? Did we do the hydrate lab last year where we heated the blue copper hydrate? Yeah? Okay. Do you remember how we had to heat it? Yeah? What happened to that hydrate when we heated it? Like, wait, tell your partner what a hydrate is. What is a hydrate? What's this? What's this?
Crystal lattice.
This is a crystal lattice. What kind of a crystal lattice, Anne? Ionic crystal lattice, okay? There are other crystal lattices. If you have a metal, that's a metallic crystal lattice. You can have molecular crystal lattices as well. Like say you have iodine molecules that are bonded via IMFs to each other. That's going to be a molecular crystal lattice. But mostly we are concerned with ionic crystal lattices. And copper sulfate would be an ionic crystal lattice. What does it mean if it is hydrated? There's water in it. Where is the water? Does that mean it's dissolved? No, what it means is that within the spaces of that ionic crystal lattice, there are gaps in there, in between the ions. Water molecules are teeny tiny, and they can fit in there. Okay? They don't do this to all salts, only some salts. What are they held there by? Intermolecular forces. Intermolecular forces, strong or weak?
Weak.
Which one? Chat with your partner. Intermolecular forces, strong or weak? Say compared with ionic bonds.
Weak.
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 Intermolecular forces are indeed weak. How about ionic bonds? Ionic bonds are strong. So, if we start to heat this, what will happen to the particles?
They will start shaking.
They will start shaking. And eventually, what's going to happen to the IMFs?
Break.
They're going to break.
There it goes.
And, yes, they will actually, the water will boil off. But what's left intact? The ionic crystal lattice. So this is one of the labs that can come up on the AP exam, okay? And it is the one where you take this and you heat it, you measure the mass before, and then you measure the mass after, and you figure out how much was water and how much was salt. Yeah? Do we heat it once? Why would you? Yeah, we heated it 3 times. Why did we heat it 3 times? To make sure that all of the water is actually gone. How would you know from your results that all the water is gone? You heat it once, you weigh it. You heat it twice, you weigh it.
You measure and it increases after.
If the mass has stopped changing, you know all the water is gone. Okay? Would you guys be able to figure out an empirical formula based on that? Figure out your moles of water. Figure out your moles of salt, right? You got the mass of water, you got the mass of the crystal, find the moles of water, find the moles of the crystal, find the ratio between the two. And if you're like, that's okay. The Cliff's Notes book has a lab section in the review books, and you can look up that lab and it'll walk you through an example. Okay? All right. So that last year, what we did was we were going in the forward direction. Okay?
We end at 19.
19, okay. So, did we last year collect all the copper hydrate, copper sulfate afterwards? Did we? I feel like maybe we didn't because it didn't work out in terms of timing and stuff. But if you put water back in, it actually gets really hot. Yes, it turns back. When you heat it, this is blue here. This one is blue. This one is white. And then if you put water back on, so if you add water back into the white stuff, it turns back to blue and it gets really hot.
What?
Yes.
How do you make sure you don't put like too much water?
Oh, it's really difficult. Usually you end up with a soupy mess. Yeah. Okay. Normally what would happen is you would just like leave it exposed to the environment and it would absorb water over time, but that takes a long time. Okay. Okay. Recap. Reversible reactions are those that can proceed in both directions. One of the directions must be endothermic and the other must be exothermic. Forward and reverse rates are the same when the system is at equilibrium. The concentration of products and reactants do not change. However, at equilibrium, the concentration of the products does not equal the concentration of the reactants. To be at equilibrium, you must be in a closed system. The position of an equilibrium can change, though, and will shift to the left or the right, depending upon the conditions. 2.1d, page 16. By the way, before we start on this, did anyone have any questions from the Blue Book? You did some exercises there. Do we have any questions from the Blue Book? How did we feel about those? Or did we not do them? How many people did them? Blue Book questions. How many people did not do the Blue Book questions? Okay, that's fair. All right. Please do the Blue Book questions because they are part of the AP curriculum, and I need to know how did we feel about those of us who did it. Okay. Are there any we would like to go over before we plunge ahead with more of this? Well, what I would like to do before I give you a practice test is I would like you to ask questions about like I would like you to ask questions. But yes, I can give you a practice test for sure. I'm going to give you some old AP questions based on rates. Okay? So I'll just wait for a minute. If you want to take a look at what you did yesterday, let me know if there's any questions from there. It was pages... Oh, and by the way, I don't know if you guys saw it. There are science opportunities that were sent to us from the Career Center. And you guys are science people, at least I assume you are. You're taking Chem 12 AP. Most of you will be. Unless you're one of those people who just wants like the breadth credit, which is also useful. Anyway, there's a whole bunch of information about them here. You can also go, I know, they just keep going and going and going and going and going. So there's a mini med school. There's Women in Orthopedics workshop. SFU Science Alive, Exploring AI, SFU STEM Speaker Series, UBC Lab Day, Quantum Communicators at UBC, BCIT Biotechnology Career Awareness Workshop. That sounds useful. Gardner High School Science Symposium. You could spend your entire year just going to these sciencey things. Woo! Take a look through them, see if there's anything you like. Any questions from page 12? The answer keys were off. Yeah, somebody told me that yesterday. They said 1.6b, 1F was wrong, and 2D, E, and F were wrong. And yeah, so I just need to fix the answer key on those ones. Okay, so if you were feeling like because the answer key was not happy, that's because I was wrong. Yes.
So it says that concentration of the
This was 1.6 what? D? C? Okay. Yeah, and number what? 2? 7. Like I'm getting everything completely wrong here. Okay. The decomp of, yeah. And the concentrations of ammonia are recorded every 10 minutes, yes?
So for the part we have
Oh yeah, it should be minute. Yeah, you're absolutely right. Unit. Anything else? I'm sorry, this is what it looks like when this is like the second go through on a book. The answer keys tend to be a little dodgy at best. Nothing else? Okay. Then let us go back to here. Do we really want? Okay. Okay. Here we have, this is page 16 in your pink book. You guys seem done. Are you done? Okay, so what I'm going to do then is I'm going to give you your homework, and you can start on it now, because I also feel kind of done. Like I'm like, I don't want to start this and get partway through it. So you are going to do in the blue book, page 13. Yep, page 13. And then page what? Yes. And page 24. To 25. Page 31. And page 38. Is good? Can live with this? It is a lot. If you're like, I only want to do one of the questions on page 13 and like none of the rest, then you can be like, I'm going to do one of the questions on page 13. If you want to do page 24 and not page 25, do just page 24. Do you know what I mean? Like make it manageable. Okay, if you got lots of time tonight, if you're like, Tuesday's my night when I have time, then do everything. But if you don't kill yourself. You got lots of courses to do.
Where should I like no, all the ones that they posted on all Yeah.